As you can see, I think it's what, like 6 different theorems and corollaries that we're learning today. These first 4, or the 4 on the front side here, they relate to one another, so they're pretty similar to one another. And then the 2 on the back are a little different. Now, I think we've used this word before, corollary, but I want to make sure we understand what this is. So it says corollary to side-splitter theorem. A corollary is just kind of a bullet point of a theorem, so it's kind of a follow-through from the theorem. It's almost like theorem whatever part 2. So this is just following from the side splitter. Okay, so following from the side splitter theorem. So first we're going to talk about what side splitter theorem is, and then our corollary is kind of a consequence of that, or a follow-through from it. Alright, so let's take a look at side splitter theorem. You've gone through and you've read these, but let's kind of translate what's happening here. Side splitter theorem says if a line is parallel to one side of a triangle and intersects the other 2 sides, then it divides those sides proportionally. So we're dealing with a triangle here. That's kind of the key thing for side splitter theorem. And we have a line running through it that is parallel to that 3rd side. So anytime we have a triangle where there's a chunk going through that's parallel to that 3rd side, then we can know the following, that our sides are proportional. So let's compare, or kind of see how that proportion is set up here. So I have segment AB compared to segment BC is equal to segment DE compared to segment CD. Okay, so that ratio of AB to BC is the same as the ratio of ED to BC. Now, as we know with proportions, we can set these up in a different order as long as you follow the same format. And that's a result of our properties of proportions that say that we can just go ahead and flip a diagonal. So, for example, if I switch this diagonal here, AB to DE is equal to BC over CD. So take a look at that. AB to DE is equal to BC over CD. Again, we went just in a different format, just in a different pattern, but we're still going to have that proportion is true. Now that'll be a different ratio, but the setup, AB to DE, will have the same ratio as BC to CD. So just like before, you might set up your proportion a little different than someone next to you, but as long as you follow the same pattern and set it up, that's fine. So let's go take a look at that classwork, that second page, and go to problem number 4. We're going to be flipping back and forth this week. So our side splitter theorem says we have a triangle with a line running through it that's parallel to our 3rd side. Here we have a triangle with a line running through it that is parallel to that 3rd side. According to that theorem, our pieces are proportional. So my pieces, I have A and 9, 15, and 5. These pieces are proportional. Again, you can set up your proportion differently than how I'm setting it up, as long as you follow the same format. So I'm going to go and say A to 9 is equal to 5 to 15. I could have done it differently. I could have said A to 5 is equal to 9 to 15. I could have done 5 to A, 15 to 9, 5 to 15, 8 to 9. As long as you follow that same pattern.
Yes. I have a question about when you're like simplifying the fractions.
Mm-hmm.
So when you're like have it set up like this, can you only simplify, like for example, the 5 to 15, or can you simplify diagonally as well?
No, you cannot cross that equal sign with simplifying. It has to be within that same fraction. That's a good question. Alright, so let's go ahead and solve for A. Regardless of which way you set it up, let's go and solve for A. Now you can cross multiply, but for this particular situation, since A is already in the numerator, I'm just going to multiply by 9. And then over here, I already have A alone. You're still welcome to cross multiply, you're just doing technically one more step than is necessary. Now again, sure you can multiply 9 times 5 and then divide that by 15, but I'm going to just deal with my factors here, so I have smaller numbers to work with and simplify what I'm able to. First of all, can we simplify 5 and 15?
Yes.
What are those both divisible by?
5.
Good, so I have left then 1 over 3. Do you agree with that?
Yes.
Okay. So now I have 1 times 9 and 3 times 1. Well, I can reduce my 3 and my 9 And that comes down to 3 over 1. So what's my final answer?
3.
3. Notice I didn't have to deal with what is 45 divided by 15. Now, that one's not too bad, right? 45 divided by 15, that's not too bad for your x-ray. But once you start getting to bigger numbers, like 258 divided by, I don't know, 16, what does that come? Alright, so this is an example of our side splitter. Again, we have a triangle where those two lines are parallel. Then I can compare my pieces. This is different than what you were doing on your homework, where on our homework, we didn't know this theorem yet. And so we had to compare our small triangle to the big triangle.
Comparing the sides.
Right now we're comparing just the pieces of the side. So before this, what we would have had to do is say, okay, my small triangle, so I'm going to go draw it separately, we have 9 and 15. And my big triangle would have been 9 plus a, and then 15, 5, 6, 20. So before when I would have set up my proportion, I would have had to do 9 over 9 plus a equals 15 over 20. I had to use the entire side. But now that we know this, as long as those are parallel, I can go and just compare the individual pieces. But again, notice that this only works with my pieces. If I wanted to compare this third side, that is the entire side length, not the pieces. So I'd have to go back to our old-fashioned way of comparing entire side lengths. Yes?
So because of this, we can do a over 5 equals to 9 over 15.
A over 5, yes. Yep, we can use those individual pieces rather than comparing the entire side lengths.
But does it only work when it has two parallel lines like on the bottom?
Yeah, so our requirements, it said given a triangle where a line is parallel to that third side. So you have to have that those two lines are parallel in order to use this. Yes?
Will the scale factor of the piece to the piece be the same as the side to the side?
That's a great question. The answer is no. So Lucy asked, will the scale factor of piece to piece be the same as scale factor side to side? No, so if they ask for the scale factor of those triangles, you want to go back to the entire triangle length as it is. So you'd find all of your information, and then I would say, for this one, it'd be 15 to 20 would be my scale factor, and then simplify that to other questions? Okay, these are great questions. So let's go ahead and take a look then at our corollary. Or sorry, not corollary, our converse. So, real quick, what is a converse again? Yeah, we flip-flop, right? We switch our hypothesis and our conclusion. So my side splitter said, if those lines are parallel, then the sides are proportional. The converse simply says, hey, if I know those sides are proportional, that means that the lines are parallel. Alright, so if I can show that these pieces are proportional, then I can know that these lines are parallel. And so that's what this is stating here. If I have that proportion, then I know the lines are parallel. So if I go back to that classwork, and you guys do like musical chairs or papers. Numbers 1 and 2 is going along with that. Determine whether the given information implies that QS is parallel to PT. So let's just go and take a look at number 1 here. Determine if these are parallel. Well, in order for my lines here to be parallel, the sides must be proportional. So let's go and set up our proportion and compare. So I want to know TS compared to SR. Is that the same? I'm going to put a question mark over top because I'm checking. I don't know that they are the same. I'm checking that. Is that the same as PQ to QR? Now again, you could have set up your proportion differently, which is why I always want you to label what you're doing there. And then we're going to check and see. So let's actually identify and compare our numbers. So TS was 34, SR was 50. And we're checking, is this the same as PQ, which is 35, and QR, which is 16? So let's first try simplifying the left side and then compare that with the right side. Can we reduce 34 to 50? No, can't reduce anything with it. 34 is just 2 and 17, and 15 is 3 and 5. There's actually nothing in common. Can I reduce 35 and 16?
No.
No. So these are not the same. They're not the same ratio. So my sides here are not proportional. If my sides are proportional, they cannot be parallel. So I need my sides to be proportional in order to be parallel. So determine if they are parallel. Nope. QS is not parallel to PT. And how do we know that? We know that because the sides are not proportional. I'm just going to say because, and I'm just going to list this proportion that I set up. Again, you might have done a different proportion, that's fine. But just going to say that that proportion does not work. They are not proportional. Thank you. Okay, so our side splitter theorem allows us to, when the lines are parallel, use this proportion to solve for known values. The converse allows us to identify whether or not those sides are parallel. Yes?
So we know they're not parallel because you can simplify one side.
Not just that we can't simplify it, but that they're not the same ratio. So we were trying to simplify to see if they came down both to the same thing, like 2/3 or 4/5 coming back. Neither of these fractions gives us the same value. So since those are not the same values overall, then they're not equal. So thus it's not parallel.
So one of the lines is 34 and 15.
We would have been golden. So it would have been parallel. Other questions so far? Wow, sounds like we have another person in that. Alright, so we've got side splitter and converse of that. So now let's take a look at our corollaries from there. And again, our corollaries are just kind of a follow-through from the original theorem. So my original theorem was side splitter where we had a triangle and parallel to the side. Our corollary is when we don't deal with the triangle, but rather a set of parallel lines. So 3 or more parallel lines, as you can see here on your picture, these are parallel, intersect 2 transversals. So we've got 2 transversals running through them. Then the segments intersected on the transversals are proportional. So again, what we have is those pieces are proportional. Now, let's take a look at this. So again, if all 3 lines are parallel here, then I have JK to KL is equal to ON to NM. And interestingly, that's also equal to JL over OM. We probably don't use the whole segment piece as much. We probably use those individual pieces more so. But we have it, again, the individual pieces are proportional. And what we know with proportions, we could go and take this proportion here and flip-flop my diagonal and say JK to ON is equal to KL to NM. And that's just going in a different order. So JK to ON is equal to KL to NM. So it's, again, just going in a different pattern, different order with that. So it's really like side splitter, it's just we don't have a triangle here, we're just dealing with a set of parallel lines. Now the reason why this follows from my side splitter theorem is because if we look, I can extend these out. And wouldn't this create a triangle where it has lines parallel to that third side? So that's why it comes from my side splitter theorem. It's really, instead of having a triangle, we just have a set of parallel lines, and thus our pieces are proportional. Questions with that one? Okay, so let's go ahead and turn to problem 5. So here with problem 5, we can see we don't have a triangle quite, we just have a set of parallel lines, with the lines coming here. So again, I have parallel lines. I have transversals going through it. So I know that these individual pieces are proportional. And again, you can set up your proportion in either way as long as you have that same pattern. I'm going to start off x to 8 is equal to 15 to 20. And then solve from there. And again, you could have done x to 15, 8 to 20, 20 to 8, 15 to x, 8 to x, 20 to 15. Just as long as you follow that same pattern. Alright, and then go ahead and solve for this. So I want you guys to go and solve. I'll solve up here. You can cross multiply, you can just multiply by the 8, whichever you prefer. But go ahead and solve from here.
Good.
Alright, questions on that? Again, very similar to side splitter. We're dealing with those individual pieces. It's just not creating that full triangle.
Would we use this in a proof table?
It's possible you could have it in proof, yeah. I would think that it's more common that you're probably going to be dealing with it to solve for an unknown variable, but you could be using these theorems in a proof. Alright, so that brings us down to kind of our very unique one. And this is just, I called it another corollary. It's another corollary from that side splitter theorem. That's not the title, you'd actually have to write out what this says. But this is a very specific case. So what we have is, again, 3 or more parallel lines. And we have 2 transversals going through. It doesn't really matter that the transversals meet over here. It's not necessary. But what we have is 3 sets of parallel lines and transversals going through it in such a way that this transversal gets cut congruent. So if you start off with a set of 3 parallel lines that cuts a transversal into congruent pieces, then what that means is any other transversal you draw through these are also going to get cut congruently. Now this is, notice Fi is not the same as GH, but it's equal to the other pieces along its own line. So again, I could draw any transversal through here, and these pieces would be congruent.
Are we gonna use
There we
this
go.
a lot?
No, again, this is a very specific case. You won't see it very often. So this one, again, this comes from what we did up above. So if you think about it, if I set up my ratio, wouldn't that ratio be the same? So we can still use it to solve. But it's kind of a shortcut in the sense that if we see that it cuts it into the same pieces, then we know they're going to be the same. So for example, if I told you that this was 12 and 12, and this guy was, let's say, 8, how much would this one have to be? 8. Likewise, if I gave you all that information and said this was 5, how much does that one have to be? So it's just kind of a shortcut. So you probably won't be using it very often, but it's something to note from there.
Is there no shorter way to write how to explain it? Like if we had to use it in a proof, would we have to write the whole thing?
You would need to write the whole thing. I mean, you could say 3 or more parallel lines cut a transversal congruently, cuts any transversal congruently, but honestly, you're probably not going to use this one in the proof.
Oh,
I would be surprised to see this one in the proof. At least ones that will be doing.
okay.
Yes?
Could you just say corollary number 2 to the side splitter theorem?
Now, which is it? Yes?
So, the congruent segment from the top, we can get to each other, but like the 5 and the 8 are not congruent.
Correct. So different transversals will have different pieces that were cut off from it, but I know that on the same transversal, the pieces will be congruent. So like I could draw in another parallel line here in such a way, now it would again have to be set up that if I started out with all 3 sets of parallel lines, have those same congruent pieces, then again for all these other transversals I would know that this would have to also be 8 and this would have to also be 8. So it's a very specific case, and it stems from our corollary to side splitter theorem, which stems from the side splitter. Again, because our ratios are going to end up being the same. Other questions with that? It's kind of a weird one. Okay, so let's flip it over to the back side theorems. So again, the front side, all of this stems from that side split, where we have parallel line cutting through, cuts those pieces. So now, let's take a look at these two. This first one kind of still goes along that same lines. This is just in a specific case where we have a segment whose endpoints are the midpoints of 2 sides of a triangle. So let's talk about what that is. A segment whose endpoints are the midpoints, we call that a mid-segment. So this is just a mid-segment. The mid-segment is simply a segment that joins the midpoints. Okay? So if I look here, A is my midpoint. We can see that because AD and AB are congruent. Likewise, B is my midpoint of EC because EB and BC are here. So this segment that connects those midpoints is called the mid segment. So we could just say the mid segment of a triangle rather than that whole thing. So the mid segment of a triangle is parallel to the third side, and its length is half the length of the third side. So we actually have two followers. So if I have my mid segment, I can know first of all that it's going to be parallel to that third side, and I'm going to know that it's half the length of the third side. So let's say that DC, the measure of that is 20. How much would my mid segment be? 10. So a pretty straightforward there, and that once we have our mid segment, we can know these two properties. And again, if we were to use the side splitter here, my side splitter lets me know that I could say that these are proportional, which again, that's the 1 tick mark to the 2 tick mark, 1 tick mark to the 2 tick mark. But again, notice that my mid segment itself is half the length of that third side. Alright, so I think that's almost like that. Any questions on this one? Again, that's specifically when we have that mid segment. Okay. Yes.
So if it's parallel, how do you know like the measure?
That, well, our theorem tells us that if it's the mid segment, we know two things. One, it's parallel to the third side. Two, it's half the length of the third side. And again, this is only for when we have the mid segment. So this is not true for any side splitter. The side splitter doesn't have to be the midpoint, right? I could have my side splitter cut through up here. Clearly, that's not going to be the halfway point. But when it happens to be that it is that mid segment cutting through the halfway point on either side, then I have this following property. Yes.
Does it tell you that it's the mid segment?
They might tell you it's mid segment, or they might just tell you that these two pieces are congruent and these are congruent, so you would know then that it's the midpoints that are being joined. So you just need to see that you have those midpoints joined together. Yes.
So can all these theorems be used?
Yep. You'll notice that some of them are more common than others. Like side splitter is probably the most common to be used in the but all of them could be used.
Wait, so want another corollary? You have to state the whole thing.
Yeah.
Can we just write mid segment there?
Nope.
Wait, you for this one?
Nope, you gotta write the whole thing. There's no title for this one. Now you could turn it down and say the mid segment of a triangle is parallel to the third side and half the length of the third
We
side.
should name it.
Wait, so what do you refer to it as?
You would have to write out the theory. So this is one of those terms that does not have a title. Just like a line parallel to, or two lines parallel to a line parallel, that one didn't have a title. So you have to write out what the theorem is.
That theorem.
If it does not have a title, then we will not give a title because only the ones that have titles are known as that by that title across the entire nation, and we cannot just make one up and just those in California that happens. We should not. Okay, other questions on this particular theorem?
Does it have like a number
So the number in the book would be different than another textbook. So like it would probably say 7 dash whatever because it's in chapter 7. But theorems and postulates are not numbered across the world the same way, which is why we don't use that much. Mary, did you have a question?
Do we have to write exactly?
No, you don't write the exact words. Like for this one, I would say the mid segment of a triangle is parallel to the third side, if that's what you needed. If you needed the half length, you can say a mid segment is half the length of the third side. You can short it down to what we need. Okay, so now triangle angle bisector theorem. This one is kind of its own category. Because notice with this one, I don't have any sets of parallel lines. Previously, we've been dealing with parallel lines, right? So here, the triangle angle bisector theorem, we have, if a ray bisects the angle of a triangle, oh look at that. So if we have an angle bisector within a triangle,
See, this one's easy.
so the two angles are right there.
Is
Then
already
it divides the opposite side into two segments that are proportional to the other sides of the triangle. So you got to be careful with your setup here. So if we have an angle that is bisected, so FGH is bisected, so this is my starting point. If that is true, then I have the pieces that were cut are proportional with the entire side lengths. So let's take a look at this breakdown here. FI compared to IH is equal to FG compared to HG. So notice here we are using a piece compared with an entire side. Now with properties of proportions, once again, I could go in a different pattern because I could change my diagonal here to have Fi over Fg is equal to IH over HG. And so if I were to do it in that format, instead of comparing piece to piece, side to side, I would have Fi to Fg, so piece to side equals piece to side. Now this is only true when I have that angle is bisected. Again, this is one that's different because we aren't dealing with parallel lines here. We're dealing specifically when we have an angle bisected. Yes, Mike?
Does it have to be a red?
No. You could have a line going through there, or a line segment.
So, like, it can be any type of lines or it.
As long as it cuts that angle in half.
Isn't GI a segment?
But like, how would we know if it's cut in half now?
They would have to either tell you this is an angle bisector, or they'd have the markings like we have on the diagram there, where it's one arc and one arc.
How is it?
Well, I can call any of these array. I'm just referring this to ray GI.
Okay.
That's just a continuation of it. I could say segment GI. I could say line GI. So it's whatever cuts that angle in half. You're getting hung up on the wrong stuff, guys.
Isn't this already a theorem? Like, what's the other?
Will you definition of it?
Angle bisected. Oh, wait.
That's
Some of you guys were thinking that it cut this side in half, but that's not true. Notice, guys, this is only bisecting my angle. It does not bisect the side. This is not true. In fact, most times, those are different lengths.
But isn't that another theorem that we use?
No. We never have encountered a theorem that says if an angle is bisected, the sides are equal.
But isn't that
Wait, really?
bisecting means it makes them equal?
Wait, what's segment?
Bisecting the angle. This is only bisecting the angle, not bisecting the sides.
Wait, we haven't read.
Oh, so it's not bisecting the triangle?
No. My only thing given to me is angle
Wait,
FG.
but if it was the triangle bisector, then the sides would be equal?
We don't have a such thing as a triangle bisector.
Finding a side to make triangle.
So, guys, a lot of you have been trying to do this, and I've told you it's not true on multiple occasions, but if I have a triangle, I'll try to make it a bit more extreme here so you can kind of see
Yeah, I know, right?
the extremeness of it. If I bisect the angle of a triangle, that does not automatically bisect the sides. Notice that this piece and this piece are not the same length. If I have my angles bisected, that does not bisect the opposite sides in any triangle. The only thing that tells me is that it bisects the angles. Now, from here, I can know that these sides are proportional with the segments. The pieces are proportional with the segments. That's what I know to be true. I do not know that in any triangle those pieces will be bisected. In fact, in most triangles, it is not bisected.
Wait, so
Yes, Mark?
So it's segment bisector that makes them equal?
A segment bisector would be bisecting the segment. Yeah. So if I
So
had,
then the two things would be equal?
yes, but that segment bisector is not necessarily going to go through your angle. Because that only bisects the segment.
So in this case, find the angle and then the other gives me the segment instead of bisecting the whole thing. Unless,
So for this one, we're only given that the angle is bisected.
Bisector.
I could have in this triangle, I could go over here and bisect the side. So in this triangle, I could go ahead and have a segment bisector. But that segment bisector is not necessarily going to cut my angle. In fact, guys, next unit we're going to be comparing angle bisectors with perpendicular bisectors, and Amani, perpendicular bisectors that will cut them in half. And we'll compare that with medians, which also cuts this side in half, and altitudes. And we're going to look at the properties of those and how they correspond with one another. But please understand that an angle bisector does not always bisect the other side. Angle bisector. It is only bisecting the angle. That's the only thing we know for sure. Now, when we have this happen in a triangle, what we can pull from here is that these pieces are going to be proportional. Fi to IH is proportional with FG to GH. So we know that it's going to create that proportion, but we don't know that it cuts that in half.
Oh,
So because of the third angle bisector, do we know that the angle on the top is congruent?
Third angle bisector thing, we don't have
Oh,
such.
sorry. The angle, like G, angle G, are they like equally cut in half?
It is bisected, so that means that this angle gets cut in half.
Stop it.
Now, I don't know, Samir, that F and H are the same. In fact, most likely these triangles are not going to be similar. So the only thing I know with the angles is that this angle G got cut in half, so these individual pieces are congruent. I do not have the F and H are congruent. I do not have the F, I, G, and G, H are congruent. So the triangle angle bisector only tells me if my angle is bisected in a triangle, then those pieces with the sides are proportional. That's the only thing we know. Other questions with this?
why are we doing this today?
All right, so go to your classwork, number 7 here. So again, with the triangle angle bisector, we're not dealing with parallel lines. We just simply have a triangle where one of the angles got cut in half. Here we have a triangle where one of my angles got cut in half. So we can set up that proportion. Now again, you can go in a different order just as long as you maintain that same order. So I'm going to go ahead and go 21 with its corresponding side, 33, is the same as 17.5 with its corresponding side, Q. So again, I use the piece with its corresponding side equals the piece with its corresponding side. And again, you could have set this up differently. I could have said piece to piece equals side to side. Just make sure you go in that same order. Doesn't matter which order you use as long as you maintain that format, maintain that order. Questions on our setup? I'll let you guys solve that at a later time. But I want to go ahead and move down to this problem here. So now we're going to go ahead and using this diagram identify the different pieces, which piece will complete that proportion, and also which theorem or postulate corollary we use. Now again, remember side splitter deals with the triangle, right? Our side splitter dealt with the triangle, whereas the corollary to the side splitter dealt with just a set of parallel lines. Okay, so if it makes a triangle, it's possibly side splitter. If it does not make a triangle, it's probably going to be that corollary. Alright. So for our first one, we have RS to what gives us JR to KJ. Okay, so RS to what gives us JR to KJ. What do you think is going to fill in that blank? KS. Good. Okay, so let's just go and double check real quick. So RS to KS is RJ to JK. Yeah. What theorem do you think we just used it?
Triangle, angle, bisector.
Good. Triangle, angle, bisector. We see it creates that triangle, and we have angles bisected. We did nothing with parallel lines, right? We didn't use parallel lines to solve this here. We have a triangle where the angles bisected, and we did piece to side, piece to side. So this is triangle, angle, bisector here. Okay.
Can you do that again?
Yeah.
It's okay, on to
So I'm gonna start with the proportion that was given to me. So JR to KJ is equal to RS to what?
Oh, KS.
To KS. And so we use the piece of the side that was opposite my bisected angle, and then the full side there. So I use piece to the side, piece to the side. That's the triangle. Other questions with number 25? Sam, pull that out of your ear, please. Alright, so now number 26. So KJ to JP. So KJ to JP is equal to KS to what? SQ. Now the question is, what did we use for that?
Side split.
Side splitter, good. Notice it does create that triangle. We're using a set of parallel lines within there. That is side splitter theorem. Good.
Oh.
And again, it makes that triangle, so it's kind of a hint towards side splitter.
Wait, it's just called side splitter.
Questions with that one? Okay.
So like if those parallel lines weren't there, could we say that SQ would would be proportional to KS?
For proportion, you have to have two ratios. So you've only given me one ratio, SQ to
KS.
So that's one ratio.
Oh, and KJ number 26. Like, if those parallel lines weren't there.
If we didn't know that they were parallel,
Yeah.
we would not know. That's a good question. So Faisal just asked, if I did not know that these lines were parallel, I would not have that proportion.
Is there any way to solve it then?
Nope, you have to have that the sides are parallel in order to use that proportion.
Could you not use the converse of side splitter here?
Converse lets me know that they're parallel, so you have to start off knowing your proportion. So guys, if we did not have these were parallel here, we could not set up a proportion with our pieces. What I would have to do is consider the big triangle to my small triangle and then compare the entire side length to the entire side length. When I have those parallel lines though, that's what allows me to compare piece to piece and piece to piece. Alright, I want you guys to go and try 27, 28, 29, 30. You're filling in what matches or what corresponds to that box, as well as what theorem or corollary did you use. Take a couple minutes to try that.
Oh, I got that trick.
It's in the very.
But why is that? Go through. Sam,
A minute
it's
late.
correlated to the side split.
Yes, ma'am.
It's correlated to the side split theorem.
No, I don't.
Yeah, it is.
Alright, good.
It's corollary.
Correlated to the side split. I told you.
Went up to my jacket.
So again, I want you working on 27 through 30. You're going to fill in that gray box as well as what theorem or corollary or postulate you used for that. And feel free to work with those around you.
So whatever where's K? So call me KT. Number 28 is K.
This corollary
Alright, do we need one more minute? No more minutes? 2 more minutes?
Like 2 more minutes.
Let's go 1.5. Alright, let's go and take a look at these. Alright, bring them back up front, please. Number 27, what do we get for our blank here?
JP.
JP. So QL to PM, SQ to JP. What do we think for this one? Good. Corollary
Oh, it's one off?
to side splitter theory.
Spelled in
Can you say SSR?
Corollary to side splitter theory. Now notice again, this does not complete that entire triangle. It is just the chunks in between the parallel lines.
What does corollary mean?
So corollary is a follow through from a theorem. It's kind of like theorem and then follow from that conclusion from there, or like part two.
Can we say SS theorem?
Nope, side splitter theorem. Alright, number 28, what do we get for our box there?
KP.
KP, do we agree?
Yes, sirree.
Alright, so KP.
The triangle angle.
Now we have PT to KP. Automatically, once you're doing with the piece of one side to the entire side, it's probably going to be triangle angle bisector, but let's just double check. So PT to KP, and then TQ to KQ. Notice this makes, again, that triangle. We did not use parallel lines. We used the piece and the entire side. So this is triangle, angle, bisector. Alright, do we have questions on 27 or 28?
No.
We should make a folder that has them all on this.
Alright, 29. What's our blank here?
Okay.
AM. Alright, again, let's go ahead and compare. So KL with LW. Right there, that should already be a hint as to what you're about to use. And then KM to MW. What did we use?
Triangle angle bisector theorem.
Good. Triangle, angle, bisector.
Wait, so if that angle wasn't there, we couldn't use it.
If they didn't tell me that those were congruent, then I wouldn't be able to use triangle, angle, bisector.
We wouldn't be able to use anything else.
No. You would have to go that angle. Alright, other questions on 29? Alright, so number 30, what did we get for our blank?
Yeah.
PM.
MP. For my MP.
Alright, what do we think the theorem is for this one?
Side splitter.
Give me a thumbs up if you think side splitter, thumbs down if you think it's something else. I'm stupid though.
You say I stupid.
I'm stupid though. Alright, so let's compare this one. So we have PM to KP.
I'm stupid.
Yes, enough. And then LQ to KQ. This does indeed create that entire triangle, and we are using the pieces cut off by the parallel line, so this is indeed side splitter theorem. Again, we're using pieces created by those parallel lines, but it goes all the way out to create a triangle, which is why it's side splitter rather than corollary side splitter. Alright, questions on those? Okay, go ahead and flip it over to our classroom. Now again, I know that we've done quite a few of these together, but I want you to go ahead and work individually on these problems that are remaining, both on the front and the back side. After some time, I'll go ahead and throw up our setup and our answers for this. You are welcome to work with those around you, but I don't want you getting up to move around the room to work with them. Okay, so I want you to try individually using those around you as needed. Of course, you're welcome to ask me questions as well. But go ahead and use this time to finish out the problems that we did not do on the classwork to give you some practice with it. Alright, so we're going to take a look at our answers for the first one. Or sorry, on the front side there. So for number 2, did we get that those lines were parallel?
Yes.
Good. So you should have compared your ratios and got it down to the same thing, which does indeed give us that they're parallel. Now, depending on how you set up your ratio, you might have gotten a different ratio than another person, but you should have gotten the same ratio. It's coming.
Ooh, okay. 5 equals 75. What is 75 divided by 5?
Yes, they are parallel. And once my computer responds to me, then it's going to come up over there.
You said E equals 6.
No, I said 6 because it was a
I'm not sure how to do 3.
How many times is 7?
Alright, so for number 2 here, Again, we're comparing these ratios. We get that they are the same. Now, you might have set yours up differently. That's fine. So since the sides are proportional there, those pieces are proportional. We have they are parallel. So good if you got those two parallel. 2, did we get 9?
Yes.
Yes,
Wait, for number 2?
Yes.
Which one is how? How did you do it?
Oh,
Wait, yes,
The second number.
Yes. I got that.
Oh, I just
Do we have any questions on number 2 here?
got this. Can you go through it?
Yeah. So number 2 and number 6 are a little tricky because they gave you the entire side length rather than just a piece. So I see that I can use side splitter because it is parallel lines. So we'll cut these sides proportionally. But I did not have this piece. But they told me that this was C and that the whole thing was 24. So if the whole thing's 24 and this is C, then that guy would be 24 minus C. So when you set up your side splitter, again, you can go piece to piece, piece to piece. So 24 minus C over 20 equals C over 12. Or you could, go to different format and then cross multiply. Now also, guys, you could have chosen to go back to old-fashioned comparing the small triangle to the big triangle. That would have been fine. My small triangle is still side 20 and 24 minus C. But then the big triangle would have been 24 and 32. So you could have set it that way. So 24 minus C compared to the big triangle, which is 24, equals the small triangle 20 compared to the big triangle 32. This is what we would have done before we learned our side splitter theory. So you could have gone back to that, that's fine, or done the pieces. Other questions with number 2? So number 6 was similar in that you had to deal with 25 minus Z, but we should have gotten Z equals 15 for that. Did we get that?
I 75 over.
Do we have questions on number 6 in our setup for that?
What's wrong with you?
Yeah, so number 6 here, again, we have the individual pieces. So if the whole thing is 25 and this is C, then my remaining piece here would be 25 minus C. So then when I set up my proportion, so D, actually let me set up differently than here. So I have 25 minus Z to 8 equals Z, and then you cross. Other questions on number 6 there? Alright, while I pass out your homework to you, I'm going to show you the back side. The key for this is up on Blackboard, so you can double check your work if you didn't get a chance to check.
4, 5, 6,
So your homework is worksheet 4, but remember what else is due Thursday? E-card.
Yeah.